Yeah, yes. Go ahead.
Okay. Wait. How do I? Yeah. Can I see my screen?
Yes.
Yeah. So hello, my name is Soresh, and today I'll be talking about renewable energy. The professor talked about wind energy, but I'll be talking about the tidal and the wave energy. So before we start talking about the tidal and the wave energy, what are tides? It's very simple. Everyone knows what tides are. Everyone has seen them. I'm pretty sure everyone has seen them once in their lives. But still, the tide is the periodic rising and falling of the water that results from the gravitational attraction of the moon and the sun. So basically, all the tides that you see on sea or on ocean are basically just the motion of the water because of how gravitationally attracted they are to the sun or the moon. A fun fact that I found through the slides was that the solar tidal force is 46% as large as the lunar, which means the moon plays a big part in the formation of tides and the formation of tide cycles. And that is how we can use the moon cycles and the placement of moons to actually track the tide cycles. Characteristics of tidal energy, a very key characteristic that separates tidal energy with the other forms of renewable energy is the fact that tidal energy is concentrated and it's very predictable. So with concentration, it means that you can find places where you can actually place a machinery to extract all the energy. You do not have to find a lot of place as in the wind farms. You don't have to struggle for a lot of extra machinery. You can find small streams, small straits, as can be seen in the bottom right image, where you can use the tides, where you can use the flow of the water to harness the energy. In terms of predictability, with all the weather software we have right now, weather forecasting systems we have right now, we can predict what the tides will be, how long the tide cycles will be, and through that we can use we can use those data to actually calculate the amount of power we can harness from it. So we do not have to depend on luck or chance when we have to harness energy as we have to do in terms of solar and wind, because we cannot predict where the sun when the sun will be at its peak, or whether there will be clouds, whether there won't be any clouds, whether there will be wind or whether there won't be any wind. So there is a very high chance of predictability in terms of tidal energy, because we can, based on the moon cycles and the sun cycles, we can predict where the tides and how long the tide cycles will be. And through that, we can actually calculate and harness the tidal energy in a much more efficient way. So there are basically two ways in which tidal energy is captured. One is the tidal barrage, which is the dam. The main principle in this is using potential energy, and the second is a tidal stream capturing. The main principle used in this is the use of kinetic energy. So talking about tidal dam, yeah. So in this, we basically use the inflow and outflow of the tides, as can be seen in the picture on the right. When the tide is incoming or outgoing, there is a height difference. The height difference leads the water to go from the left side to the right side when the tide is coming in, and it is the opposite. So the water goes from the right side to the left side when the tide is outgoing. So whenever there is this motion of water because of the height differences, it usually, the water is passed through a turbine. The motion of the water causes the turbine to spin, which again is how electricity is generated. And we can use the formula shown on the left to actually calculate the power output using the potential energy. This is one example of a dam used in a real life, where we can use the height differences or the motion of the tide to generate electricity, and it does not hamper any human life or human processes as well. So comparing different kinds of dams, as you can see in this table, throughout the years, the size and the power output of the dams has increased. So from in China, the dam creating 6 million kilowatt per hour per year output to the South Korean one, which produces 552.7 million kilowatt per hour per year output. We can see that with size, with different sluice gates, with different generators, the output has increased. But one limitation to dams is that it's very expensive, and it's extremely huge, and we need to, for this particular application, we need to find specific places that not only has a good tidal flow, but also make sure that it does not affect human and animal life. Not only is it expensive, but it's very expensive to find places that can be used for specifically dam purposes. This talks about the dam that is established in Korea. We saw that in the last slide as well. And there was another project that was supposed to inaugurate in 2014, but it was cancelled because of environmental and ecological issues. So this shows that when we are implementing a dam to capture tidal energy, first of all, we need to be considerate of the space that it requires. We need to be considerate of the tidal flows that the place has. Also, we need to be considerate of the fact that implementing or constructing a dam does not have any environmental or ecological issues. So this specific application of tidal energy is very dicey. So this leads to the development of various other kinds of ways to capture tidal energy. This project called the Pelamis is not an onshore project. It's basically a snake-like figure, as you can see on the picture, that is usually stranded in the middle of the ocean or middle of the sea. And it uses the kinetic motion of the waves, which causes the entire structure to go up and down, as can be seen from the side view. This up and down motion causes pistons in it to compress and expand the liquid, which is used to turn turbines inside, which again produces electricity. I'll show you the videos later on. I'll just go through the slides quickly. Then we have a buoy. This is also an offshore establishment where these buoys are in water, and each buoy contains a pump that rises and falls with the motion of the buoy, which is again led by the motion of the wave. The pump then compresses liquid inside, which then turns the turbine, which then produces the energy, produces electricity. This is a very interesting offshore/onshore project. This is the Oyster Wave Energy Converter. So how energy in this is generated is it again uses the kinetic energy of the wave. The kinetic energy of the wave causes the entire structure on the left, as you can see, to move back and forth. This back and forth motion of the flap causes the piston to move back and forth as well. The piston then compresses the liquid, and as you can see from the high pressure flow line, that liquid goes back to the onshore plant, which is then used to turn the turbine, which then creates electricity. So as earlier projects were completely offshore, this is an onshore and an offshore project. Talking about anchored buoys, this again is a hybrid onshore and offshore project. In this, the buoy is anchored at the seabed. The motion of the wave causes the buoy to go up and down, and there is a weight attached to the cable. And as the buoy goes up and down, it causes a motor to spin, which again which generates electricity. Now, this overtopping wave, the Wave Dragon, is a completely offshore project again. In this, the wave will eventually rise over the establishment. There is a turbine inside. The water will go inside and it will exit through at the bottom. And this, as the water goes in through the turbine, it will cause it to move, it will cause it to rotate, and then it will cause that will lead to the generation of the electricity. And this is another onshore establishment. This is basically using air pockets and how waves come in and go. which will compress the air pocket inside. As the waves go in, it will compress the air column, which will cause the wind turbine to spin, and that generates electricity. As the wave goes back, the air column increases, so it essentially is a vacuum, so the air is sucked out, and then it again causes the turbine to spin, and it generates electricity. So going back to showing the videos. So as you can see, this is a sideway view of the Pelamis. It's a snake-like structure, and it is a very long structure. So multiple waves can pass through the entire length. As the waves pass through it, all the small compartments of the Pelamis will go up and down. And as these compartments go up and down, there are two pistons that attach each of the compartments. As one goes up and one goes down, one piston compresses, the other piston expands. And as the motion goes back, the other piston compresses and the top piston expands. So this compression and expansion of the liquid inside is what is used to turn the turbine inside and generate electricity. So this video shows how the oyster plantation works and generates electricity.
Shorishi, can you turn on the caption?
Sorry?
Caption. There should be a wording from outside of speech.
Or did I not share sound? Okay.
Sound is not showing.
Can you guys hear it now?
Yes.
In the world, wave energy
Also, caption, please. Caption. Turn on the.
I can't hear you, Professor.
Can you turn on the closed caption of the?
Oh, okay. Okay.
has unveiled ambitious plans to develop what could become the world's first ever fully commercial wave energy farm. Using their oyster wave energy technology, they plan to capture the abundant energy in near-shore waves and transform it into clean, green electricity. The oyster wave energy devices will be located around half a kilometer from shore, in waters around 10 meters deep, and will be connected via subsea pipeline to an onshore hydroelectric generating plant. The oyster devices are simple, buoyant hinged flaps, which are attached to the seabed and pitch backwards and forwards in the near-shore waves. The machines are equipped with two vertical cylinders, each of which pumps high-pressure fresh water on both the forward and the backward stroke. This high-pressure water is then transported via a closed-loop subsea pipeline to an onshore power plant which uses tried and tested hydroelectric turbines to generate clean electricity on dry land. Each device is mounted on a piled foundation, drilled into the seabed by a jack-up barge. The buoyant flap can be towed out to the wave farm using a conventional workboat and is then lowered down onto its foundation, a quick and simple process which can be reversed to allow easy removal as and when maintenance or replacement is required. Economies of scale can be achieved through connecting multiple devices via shared pipelines to a single generating station. This also helps even out the power fluctuations of the individual machines. The Oyster devices have a certified design life of 20 years. Aquamarine Power's site on Lewis has the potential to become the world's largest wave energy farm. The company's received all required permits and consents from the Western Isles Council and the Scottish Government to install up to 50 devices along the coast at their site near Fivepenny Borv on the island's exposed west coast. Aquamarine Power believes wave energy presents a tremendous economic opportunity to local communities, Scotland and the UK, and it has the potential to make a major contribution to the world's green energy targets.
So we have seen onshore establishments, we have seen offshore establishments, we have seen dams, we have seen wind that is wind turbines that is driven by waves. We have seen flaps that is driven by waves. We have seen snake-like contraptions capturing the kinetic motion of the waves. But each of them have their own disadvantages and advantages. Onshore being a very highly adapted solution, I personally believe that to capture wave energy, the future developments or future innovation in this field would all be offshore. So instead of having an onshore and an offshore system like the Oyster Farm had, this one particular company has developed a machine that will harness the kinetic motion of the waves and convert it into electricity. And the entire machine is basically an underwater wind turbine, and it is developed in such a way that it can float on the water surface and be left offshore. And it has a very minimally invasive strategy. It can be controlled offshore and onshore. So to harness the tidal or wave energy completely, I believe that the future of future innovations have to be in such a way that the machinery is set inside the ocean or on the surface of the water. And just to show you the video of it.
This massive tidal turbine is about to be activated, so it can start supplying power to thousands of homes in the United Kingdom. The idea of harnessing power from oceans and tides isn't exactly new. Depending on how you look at it, it's really been going on for centuries. Your basic water wheel uses the force of flowing water to generate power. But what I want to talk about today is a little more powerful than that. This is the O2, and the company behind it calls it the most powerful tidal turbine in the world. It was designed and built by a Scottish engineering firm called Orbital. The O2 is a floating turbine about the size of a 747. It's 74 meters long with arms that reach 18 meters below the surface. The O2 weighs in at about 680 tons, and those rotors are 20 meters each, sweeping an area more than 600 square meters. Orbital just delivered the first O2 to the Orkney Islands, which sit off the northeast coast of Scotland. If Orkney sounds familiar, you may have caught my video on Microsoft's underwater data center. That project also happened in these same waters, and that's not a coincidence.
And Orkney's blessed with some of the biggest, strongest tidal streams in the world, so it's a pretty good proving ground. It's a pretty hostile sea that surrounds it.
That is Orbital CEO Andrew Scott. He says the O2 can generate enough clean energy to power around 2,000 homes. So let's look at how it works. The tube structure floats on the surface and is moored by an anchoring system. Inside that, you'll find most of the electrical equipment. At the end of those legs I mentioned earlier are the rotors, which are pushed by the force of the tides to generate power. And the blades can be reversed in pitch in between tide cycles. That means they can generate power whichever way the tide is moving. The produced power is sent through massive cables back to shore and into the grid. So what about maintaining those underwater cells? This is where the O2 design becomes really cost efficient.
There's kind of a rule of thumb generally in offshore engineering. Doing a job onshore costs $1. It'll cost you maybe $100 to do it offshore at the surface, and then it will probably cost you $10,000 to do it at the bottom of the seabed.
And that is why those legs are built on a hinge, so they can be brought up to the surface. That way they don't have to send divers down to do any needed repairs. Deploying the O2 is pretty simple as well. Scott says it can be towed to its site by simple small tugboats, which are relatively inexpensive.
So once the anchors and the mooring lines are in place and the cables being laid, and again that can be done fairly simply and cheaply, is that we can, I always kick myself for using the word just. It's never quite that simple, but effectively we can just throw the turbine onto site, connect it to its moorings, connect it to its grid, and away it goes.
So let's talk about the advantages of using tidal streams to generate electricity. Tides are packed with tons of potential energy. Some tidal streams are as much as 40 or 50 meters deep.
Seawater is over 800 times the density of air. So, you know, moving water at 4 meters a second is massively energy dense.
And because there's so much energy in such a small space, that's why the turbine blades can be so much smaller than the ones you'd find on a typical wind turbine. Another major benefit is that tides are predictable. Unlike solar and wind power, tidal streams aren't affected by the elements. As long as the moon is up in the sky, we know exactly how strong a tide will be at any given time. And if you're asking, how do we know this tech works? Well, Orbital has already proven it. The company successfully tested its prototype model in the Orkney Islands a few years ago. As exciting as this project is, Scott admits that it's not going to be that silver bullet to solve the energy crisis and solve climate change. He says that the O2 is designed to work in conjunction to complement things like solar power and wind power. So if you think that the O2 can be a viable solution to produce clean, renewable energy, drop a wave in the comments.
So this covers my presentation. We went through what tides are. We went through how conventional mechanisms capture tidal energy and convert it to electricity. We then saw different kinds of dams. We compared onshore and offshore establishments, and we saw what the future of tidal energy machines are like. Thank you for paying attention.